Hello everybody, I am Ben from Team Panic, and today we're going to be talking about Melty Brains. Now, we're talking about Melty Brains because of Nuts 2. Now, Nuts 2 is a robot that's currently fighting in Robot Wars, or has just fought a couple of weeks ago in Robot Wars, and it used Melty Brain technology as part of its design. Now, I've been doing a little bit of looking into Melty Brain stuff, and I'm just about to start work on my own Melty Brain, so I thought I'd kind of run over some of the basics of Melty Brains, what they are, and why you would even want to do this. So a Melty Brain is typically a round robot, but it can be a different shape. But the idea is that the Melty Brain gets its entire body spinning, typically with a weapon edge or a thwack type style weapon on it, gets its whole body spinning as fast as it possibly can, and then it can translate while spinning. So it can translate back and forth, left and right, all while spinning at a very high speed, which basically turns your entire weight into a weapon. So that is one of the reasons why people do this, or people want to do this, is for an ant weight robot like this, which is 150 grams, it means that your weapon is 150 grams. And if you can get the thing spinning fast enough, it hits with a really good punch. Because of course, as I said, it's 150 grams of weapon, which is way better than anything else that you will build, because of course any other weapon system has to have a motor that may or may not be part of the weapon system and a drive system which is going to take away the weapon weight. In a Melty Brain's case, your drive system, your chassis, everything, your electronics, your battery, all of that is going into the hit, which means you have more mass behind each and every hit. Now, there are reasons that people don't want to do this, and one of the big ones is the name is a Melty Brain because these things melt your brain when you try and work out exactly how this control mechanism works. As I said, the idea is to have this thing spinning as fast as possible and then still have it move. And you can do this by turning the motors on and off in a very specific timing and setup, and we're going to get into all of that and how that is actually done in this video. But the main thing that you actually need is one of these. Now, this is actually a little bit more than what you really need. This is a 10 degree of freedom inertial measurement unit, which has a gyroscope, an accelerometer, and a magnetometer in it. A lot of people who have built Melty Brains in the past have only used an accelerometer, and once again, we'll talk about that in half a second. So, as I said, this thing, and the whole idea behind a Melty Brain is hitting with that huge weapon weight. Now, that in itself can be an advantage, but it can also be a disadvantage. So let's just take a quick look at the maths behind why this would be a good idea and why it wouldn't be a good idea. So one of the things we are looking at when we're designing and building weapons is kinetic energy. Now, kinetic energy is an equation which is 1/2 mv squared. Now, mv squared is the mass or the weight of the object that is moving and the velocity that it's moving at. So, as you can see, when you're spinning a weapon, you're building up kinetic energy. That's what all of these weapons are. Spinning weapons are kinetic energy weapons. They build kinetic energy typically by having a decent amount of mass spinning very quickly. And the faster you spin it, as you can see, the more kinetic energy you have. And when you hit something, all of that kinetic energy gets transferred, or a good portion of it gets transferred, and that is what does the damage in this case. So there is, as you can see, there are two relationships here. You've got kinetic energy, which is proportional to mass, and you have kinetic energy, which is proportional to velocity squared. So the reasons for building a Melty Brain like this is you can significantly increase your mass. You are talking a difference of, kind of 4 times or higher your mass in terms of an ant weight robot or something along those lines. And the reason for not doing it is that it is very complicated to do, and also a Melty Brain is going to spin slower than a standard spinning weapon. So when you've got ant weights with tiny little brushless motors in them, which is something that's happened in the last few years, the velocities of those weapons can easily get into the thousands of RPM, and a Melty Brain is going to have a hard time getting up to that style of velocity because it's being driven by drive motors, and the control electronics have to be able to keep up with that, when you're going up into the thousands of RPM range, your controller has to be able to track at least 8 points, if not more, around the circle at thousands of RPM, which means your controller is thinking very, very, very quickly. And that gets both complicated in programming and expensive in terms of actual controllers to run. So from this equation, as I said, we can see that by increasing the mass of our weapon, which is what we're doing when we're building a Melty Brain, we do get more kinetic energy out if we could keep the same velocity. And 10 years ago, 5 years ago, when small brushless motors weren't really a thing, a Melty Brain would have really had that impact because the velocities would have been relatively similar, not super similar, but relatively similar. So increasing this mass 4 times would actually have a huge, huge impact and a huge deal in this case, and mean that your kinetic energy is actually pushing a lot higher. As I said, in this, with the current setup with these new brushless motors, the velocity of those weapons is always going to be higher, especially in ant and beetle weights, than you can do with a Melty Brain. But with something like nuts has a very huge mass comparatively to all of the drum spinners and everything else going on in Robot Wars, and its velocity is not that bad, realistically, on the whole. I mean, it may still be hitting with less force or less kinetic energy, I should say, than those other robots with drum spinners and bar spinners and all of that kind of stuff. But that huge improvement is in that mass. Okay, so that's enough about why you would want to do this thing. Sometimes the reason for why is just because this is really cool. And that's exactly the reason I'm pursuing this. I really like the idea of a Melty Brain, and I just want to build one. So how do these things actually work? Why are they called Melty Brains? Well, as I said before, the Melty Brain is because trying to work out the control circuit for this, or the control logic for this, is quite complicated when you first look at it. But I've been looking at these things for a little while, and as far as I understand it, I think I have a good enough idea as to show you what and how these things work. So for now, what we're going to have to assume is that we've mounted a light up on the front of the robot up here. And from now on, this is going to be the front-facing direction on our robot. And by front-facing, I mean this is kind of, I think you can almost think about this as the hand of a clock. This is the minute hand. We're going to ignore the hour hand on the clock. And this is the minute hand. This is the way the robot is facing. But this is going to spin round in this entire circle, but where this is pointing is going to be 0 for now. So when these things spin up, the idea is that you turn the light, which is our little bubble on the front here, you turn it on kind of between here and about here. So if we say that's 5 degrees, then this is kind of 325 degrees. So we're going to count from here and go round clockwise. So we're going to turn on between 325 and 5 degrees, crossing over that 0 point. And this gives us our, like I said, our 0 direction. Basically, this 0 direction will be set by the direction that the robot is powered up in. And in this case, like I said, I've just pointed that arrow forwards. But if I had kind of done that, then that is our 0 direction on our robot, because I've powered it up in this particular orientation. So now that we have a 0 direction, we have 2 basic modes that the robot can run in. One is spinning on the spot mode, which is the easiest one, and the second one is translating, which is the difficult one. So in the first mode, what we're going to do is just look over here. So in the first mode, we've got a circle. This is our robot, and basically to spin on the spot, all you need to do is turn both motors on at the same time for the same amount of time. So you have one motor on at one side and one motor on at the other side at the same time. So this is just 2 small little bits. And as you can see, if we put the robot down here, what we would do is, as the robot is turning, so as the robot gets to this, which is I think probably about 320, we turn the motors on, and we turn them on all the way over until we get to about 10 degrees, and then that is going to keep the robot spinning in a circle, because basically these 2 motors are going to force the robot around in a circle just like that. And basically that's all you need to do to keep it spinning in the same direction, is you force the motors to turn on at the same time And that does mean that they're going to be turning on at different points in the rotation relative to each other, but they turn on at the same time and keep the robot going round and round and round in a circle, just like that. So this is quite a simple thing to do, and the speed control on this is ridiculously easy. All you need to do is extend the length of time that the motors are on to increase the speed that the robot is spinning. So these interior arrows are a shorter period of time, which means the robot spins at a slower speed, and the exterior ones are longer and turn on more, which means that the robot gets more acceleration around the outside of the circle and it goes faster. So that's the first mode. The second mode is the translation. Now, the translation, we need to get into some first year physics from university, or maybe some high school physics, depending on where you are and what's being taught in your high school physics classes. So, in this case, we're going to assume that the up direction, the up arrow that I'm pointing this way, this is the 0 degrees mark. And that what we want to do is we want to translate up. We want to translate up towards that 0 degrees mark. Now, the way we do this is, rather than what we did in number 1, where we turn both motors on at the same time, in the 2, we turn both motors on at the same point in the rotation. In this case, we turn the motors on at 180 degrees and turn the motors off at 360/0 degrees. So that means the motor is on all the way around the outside here, and that's both motors. Both motors do that, which means that they're not on at the same time. In fact, it means that with 2 motors, you're only using 1 motor at any given time. So right now, if I had this robot spinning, this motor would be turning on, and it would stay turned on until we get to this point, at which time this motor turns off, and this motor turns on because it's just hit the start of what we said to turn the motors on for. And then we'd turn another 180 degrees, and as you can see, this motor is still turned on. It's still in our little pathway. And then when we get all the way around to here, which is 180 degrees out from where we were, this motor at the top turns off, this motor at the bottom turns on, and it keeps going. Now, it wouldn't be spinning on the spot, it would be translating out this way, and the reason for that, as I mentioned before, is high school physics. So I'm just going to get rid of our little power on line so that I can show you what I mean by this. Basically, we can look at the velocity that these motors are imparting as vectored velocities. So at the 90 degree point, or the 270 degree point out here, all of the velocity from that wheel is pointing out in this direction. But if we take any other point on the wheel, on the arc around this way, what you'll see is that you get some velocity in this direction. Well, actually, what you get is a tangential velocity. I should draw my tangentials in first. So what you get is you get a tangential velocity, which goes that way, which is the same as up here. When you look at the 270 degree point, this is a tangential velocity. It just so happens that this tangential velocity is pointing towards the 0 degree mark, which is where we want to go. Now, the tangential velocity at any point, like I said, this is just a random point down here that I've just decided on. That can be broken down into component velocities. Now, our components in this case are a small amount in the direction we want to go, and then some in the direction that we don't want to go. So there you go. That's our little component velocities. Like I said, these are a thing from high school physics, which you can do. You can break down any given velocity into component velocities. In this case, we're going some in our 0 direction and some out away from our 0 direction. However, I've chosen this point here between the 180 and 270, but if I choose another point between 270 and 360, I choose a point up here, what we'll then find is, once again, there will be tangential velocity based on the wheel turning on or being on around this point of the circle. But once again, this can be broken down, and it can be broken down into a component going to the right in this instance, and then also some going forwards, just like this. Now, this can be done for every single point between the turn on and the turn off. But what you actually find is when you do all of that and add up all of your component velocities, the bits that go right here and the bits that go left cancel each other out, and what you end up with is velocity in that direction, which means that while this robot would keep spinning, it would definitely move up towards our 0 point. Now, we don't have to have this 0 point as our direction to move forwards. There is absolutely nothing stopping us from going across this way. But to do that, you need to turn on 180 degrees away from where you are and turn off. So you turn on here, turn the motors on all the way until you get to the direction that you want to go, and you turn the motors off. And once again, if you do the component velocities across that arc, what you'll find is a very large, well, you'll find a amount of velocity that takes you across to the right. So this is the other powerful thing about a Melty Brain robot, is that the steering system is very, very unique. You can translate any way you like. All you need to do is pick your angle that you want to travel. So I could decide I want to travel this way, and once again, all I'd need to do, turn on 180 degrees away, turn off when I actually get to the direction I want to travel. Right? So that's exactly what this would do, which means that one of the powers of this system is you can build a robot that strafes left and right, and it can drive forwards and backwards fine, and it will strafe left and right, and it can go in diagonals, and basically you end up getting almost what mechanism wheels would do out of a robot that doesn't even actually have gearboxes. This one, as you can see, I have just slapped these wheels directly on the output shaft of the motor because we want this robot spinning as fast as possible. So gearboxes, all they're going to do is slow us down. And there you go. That is the absolute power of this system. You can translate any which way you like, as long as you're set up to do it, and as long as you've got the code to do it, and you have your controller set up to do it. Now, this is the final thing I did want to mention here. Control over these robots is difficult. And there is a system out there called OpenMelt, which I will link in the description down below. It is an open source Melty Brain platform, and it has already got some mapping to take a controller and be able to do some of this stuff with it. Now, the problem with any control system for these is that there is a trade-off. So if you look at a traditional and very typical controller, which is what I've got right here, you have a couple of different options in your stick. So you've got forwards, backwards, left and right on one stick, you've got a throttle on the other stick, and you've got a left and a right on your throttle stick as well. So this doesn't lead itself to a lot of options. The throttle you absolutely need to leave as a throttle in this case. This needs to tell the robot how fast it needs to be spinning at any given time. Basically just a safety thing. You need to be able to tell the robot stop spinning, and one of the best ways to do that is with the throttle. And then also, if you want to, you can then change your speed during a fight, which is always a good thing. It's always a good idea to have speed control over your weapons. Even with a regular conventional spinning weapon, you do want this speed control over your weapon. So that is locked. That's what you need this throttle for. You need that for your spin position. Now, you then need to work out how you're going to do, or how you're going to tell the robot which direction it's translating in, and also where its 0 point is. Because if your control circuitry has even got a slight error in it, your 0 point where you started the robot, so in our case we started the robot facing up the screen like that, but if this chip has any errors in it at all, which every chip does, every real world chip has an error, as the battle wears on, you'll find that your 0 point, or the 0 point your robot thinks is 0, starts to drift around the circle, which means you need some way of telling the robot, no, correct for that, and your 0 point is back over here and facing that way. Now, in OpenMelt, what they've actually done to get around this issue is that forwards and backwards translates the robot in one direction towards the 0 point or away from it, like this, and then the left and the right stick, rather than translating 90 degrees away from 0, or the other way, it actually tilts that 0 point. So it basically ends up being controlled very similarly to every combat robot you've ever done. It ends up feeling like tank steering because you've got a forwards and a backwards, and then when you hit the stick, the robot turns, it changes its angle that it will go forwards at. So this is a quite clever solution, and it does mean that people who have never or who are used to running tank steering would actually feel right at home using this Melty Brain. Personally, I do like this idea, but I do also want to try and do something where forwards translates the robot forwards, backwards translates the robot backwards, left translates the robot left, and right translates the robot right. I know I've just done those the wrong way around, but I do want to try and do that, which does leave me with the issue as to where I put this system that I was talking about to reorient the 0 point on the robot. So I think I'm going to be not using the conventional RC stuff, and I think I will actually be using my own Arduino control box. This thing has a joystick on it and a potentiometer to do the throttle. I'm going to add 2 extra buttons up the top here. One is going to be orient left, and one is going to be orient right, and that's just going to cause the robot to incrementally change its orientation just so that I can keep the 0 point facing the way I want it to face and still have everything work. So there you go. This has probably been a little bit longer of a video than I was expecting, but that is the basics of Melty Brains. They are a complicated beastie, so I wanted to get that out there, lay that down for you guys so that you could see what this thing is and what it's all about, and then we're actually going to jump on in and build one of our own in the next few weeks. So I hope you guys have enjoyed that one, and I will see you in the next video.